And as I first say in the class, eventually imaging is about contrast. Okay, how do we perceive, understand the object from the rest of the world is really about generation of contrast. So imaging, we can define this way. The process of mapping a certain physical property or even chemical property of the object, and you want to display it in a visual form. So there's some property you want to actually visualize, and that property we call as a contrast mechanism. So for us, what kind of contrast mechanism could be important to visualize? For example, like absorption property of the light or pigment of the object, such as light imaging, typical bright field microscope, we are depending on this absorption of the sample. Or even X-ray is absorption of the bone, especially. What about scattering as a property? For example, cellular organelle has a scattering, and that reveals the presence and shape of the organelle. Then we are using scattering as a contrast. A good example is phase contrast microscope. And sometimes we want to tag with the fluorescence level to, let's say, mitochondria or DNA. Then we are using fluorescence imaging. Then we are using fluorescence emission as a contrast mechanism. Or sometimes we are using ultrasound or photography. Typically, you are depending on the reflection light from the surface, and then we visualize the surface of an object. So we are depending on using reflectivity of an object as a contrast mechanism. So typically in microscope, we are interested in intrinsic nature of the specimen, especially absorption nature, scattering nature, and sometimes emission of specific target or quantities of our interest. Here I want to explain one note about resolution versus contrast in optical imaging. So when we call resolution, is really fundamental nature of the optical instrument itself. While when you prepare your sample, let's say you have poorly stained the sample fluorescence that it doesn't show up. It's irrelevant to the microscope, okay? But you have a poor image and you cannot distinguish that has poor contrast. So in that regard, contrast is not only depending on the instrument or microscope, but also sample. So that's what I want to focus. Let me summarize today's, this week's of 1 week, but this can be a semester course of biomedical optics. We start with a nature of the light with a particle wave duality. This sets a fundamental limitation of our imaging resolution and the characteristic of light refraction, diffraction, and interference. These diffraction and interference is how we can form an image in a microscope and your retina, how you are seeing the world. And for that, we need to understand light and tissue interaction, especially scattering, and what wavelength of the light would be great for us to image underneath the tissue that we call near infrared window. And we have done geometric optics from refraction to generate a simplest geometric optics using simple lens, which is, of course, your eye does this all the time, and talking about real and virtual image. And I showed you how optical microscopy works, especially diffraction and interference, and how to get high resolution, because resolution depends on numerical aperture. And I showed you how to define resolution based on the point spread function and image characteristic as signal, contrast, SNR, CNR, and field of view, frame rate. And eventually, everything about imaging, not only optics, is really about contrast. We want to extract the information of the certain physical property to make sense to us that we call contrast mechanism. All right, thank you very much for your attention.